Okay. Okay. So, any questions as we get started here? No? Moment? Okay. So, let's see. So today we would like to talk a little bit more about these counting methods. Sometimes it's called combinatorics. And in general, right, what you do is to find or count the total number of possibilities. Combinatorics, counting. You identify the number of stages. You identify the total possibilities at each stage, and then you just multiply, and then that's like the total possibilities. There are actually three special cases, and the third one is the one that we really encounter in the binomial distribution. But really, the first one is sometimes called an arrangement. So you have n items, and you place all of them in a particular order. And so that's basically factorial, because there's n items, so there's n stages. Okay, and then at each stage, in the first stage, you pick the first one, and then at the next stage, well, the first one's already used up, so it's n minus 1 are remaining. So then at the next stage, the first two have already been picked and placed in first place 1 and place number 2, and so there's n minus 2 left, so you have that many possibilities, and all the way down to 1, where you've used all of them. And so by definition, 1 factorial is 1, and then also there's the convention, or there's a way to sort of prove that the 0 factorial is also 1. I mean, if you're interested, there's this other very interesting function called the gamma function, and there's a way to associate the gamma function with this kind of permutation on the integers. So the gamma function is defined, I think, on all complex numbers, but if you restrict it to the integers, it can behave like the factorial function on integers, and so that's where the gamma function has the property that 0 is 1, and so or the equivalent of 0 factorial is 1, and so that's where we kind of officially define that. So it's not just this random definition. Another special case is where sometimes it's called the permutation, and basically you have n items, but instead of taking all of them and using all of them in the arrangement, you take some subset R, and then you do put them in a particular order. And so one of the sort of canonical, or one of the typical examples, is officers of a club, right? Because you pick the first one is the president, second one is the vice president, third one the secretary, fourth one treasurer, and so on down, however many specific places you have. And so that would be the NPR. And then the final one is where you basically take a subset. You have, again, this larger number. You take a subset, and the order does not matter. And so, again, the canonical or the typical example is a subcommittee, because you just care about who the 5 people are. You don't care, I picked so-and-so first and so-and-so second, third, fourth. Doesn't matter the order. It just matters whether they were selected or not. And so that's the combinations. Then we want to see if we can sort of dig in a little bit more to this binomial expansion formula. Oftentimes in finance, they use this summation symbol, and really it's just a compact notation, which means that this pattern is just repeated from R equals, sometimes it's K or I or J, some indexing or some counter variable. Here, our calculator uses R, and so we will use R just to be a little bit more consistent with the calculator. And again, I think I may have mentioned this before, this is how the combination function is on our calculator, but some books, like maybe our book, uses this notation. So it really is the same thing. And really, this is what it is in its full glory. So it's got this permutation thing, and then it's got these other things over there. Okay, and then of course we want to apply this to the binomial distribution, and then we know that n is a number of times a binary. Sometimes it's also called a Bernoulli experiment, or is repeated. Sometimes each one is called an experiment, or each one is called a trial toss. If you're talking about coin P, it's a probability of success, and of course Q is equal to 1 minus P. I guess I should say that. You know, Q equal 1 minus P is the complement. And then each individual experiment is independent of all the others, and the probability of success is a constant for all of the experiments or trials, right? And so we can look at maybe this little gallery of probability mass function and continuous distribution function. So we'll look at a gallery maybe of the one of the subfamilies of this larger family of the binomial distribution. Yeah. So some of the material is here under the text, but it's really sort of standard treatment, right? In order to satisfy graduation requirements, a student must take one course from the following three, right? How many transcripts are possible? And so in general, right, what you do is you identify the number of stages. So must take one course each from the following three groups, right? So how many stages are there? There's the 3 stages, 2, 3. One is for humanities, and then one is for lab, and one is for reasoning. And then you identify the total possibilities at each stage. So for humanities, there were 10. For lab science, there were 2. And for reasoning, there were 5. So you multiply those together, and you get 100 like we did before, right? Modified, right? Take 2 humanities courses and one from each of the other 2. So you have to take 2 humanities courses. So you have humanities course 1, humanities course 2. Those are the different stages. You have to take the lab and the reasoning. So the lab and the reasoning didn't change, right? The first choice, that didn't change. And so now you realize, oh, you cannot take the same course and receive credit for it on your transcript, right? So it goes down to the n-1. Okay, and so then we saw that that was 900. So that's just a reminder of the sort of steps or algorithm that you would follow in order to do the combinatorics, in order to find the number of ways. Okay. So now we come to say some of the special cases, maybe an arrangement and permutation. So sometimes people say an arrangement is suppose you have 3 different items and you would like to arrange, you know, maybe it's implied all of them in a line in a store's display window, right? How many possible ways could you display them? And so note we're arranging all of them, right? So this way, this way, this way. And so, you know, here's what it looks like, right? If we want to apply the formal counting rules, right? There's the first one, the second one, and the third one. You know, how many possibilities are there? Well, if there's 3 things, there's 3. So after you pick the first one, there's only 2 left. And then after you pick the second one, you really don't have a choice because you're forced into there's only 1 remaining. And so you multiply those 2 together and you get 6. So here is what they all look like. On the TI calculator, the factorial is right above the multiplication, right? So you would do, say, 3 and then, second factorial, and that's 6. Okay. So now suppose that you have 5 different items and you would like to arrange all of them in the store's display window, right? How many possibilities to display them? 5 items, and you want to arrange all of them. How many ways are there? So the quick answer is, this is a special case, right? I've got 5 items and I want to arrange all of them in a line, right? So that would be 5 factorial. The general way is, you know, I have 5 items and I want to arrange all of them, okay, well, that means I've got 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. When I pick out the first one, I've got 5. All 5 of them are possible. So after I pick out that one, there's 4 remaining. So I pick out that one, there's 4 remaining. So then I picked out 2, so there's 3 remaining. So now there's 3 left. Now I've picked out 3, so there's 2 remaining. And then now I picked out 2, there's only 1. That's the default. Oh, wow, look at that, 5, 4, 3, 2, 1. I could have used factorial, right? So if you can spot that it's a special case, you can just write 5 factorial, or really, compute out 5 factorial. 5 factorial, which is 120. Okay, or you could take a few more steps, and you would still get, 5 times 4 times 3 times 2, and then I won't do times 1, right? So that's 120. Okay. Next, suppose you need to place items in some order, possibly in a storage display window. This display has only room for 3 items, but you have a total of 5 distinct items. How many possible different arrangements for this display? So you would say, well, you cannot use the factorial, right? Because the factorial means that you're going to use all 5 of them. And so we're going to take some subset of them, right? So how do we do that, right? So you could say, well, there's 3 stages, okay? And at the first stage, there's 5. And then after that, there's 4. And then after that, there's 3. And then that's all that I have room for in the display, or that's the constraint, right? So 5 times 4 is 20, and 20 times 3, so this is equal to 60, right? But you could also spot this as the permutation of 5, 3. So if you do the permutation of 5, 3, we remember the permutation is below the exclamation, below the factorial, before the exclamation point, below the factorial. So it's the shift minus. So we do 5, and then the permutation, and then we want 3. So that's 60. Okay, and so sometimes you'll see what it does is it does n p r is equal to n factorial over n minus r factorial. What it does is it does 5, and then it does 5 minus 3 factorial. So what it's doing really, 5 factorial, is it's really doing 5 factorial over 2 factorial, right? And so what is that? That's actually 5 times 4 times 3 times 2 factorial divided by 2 factorial. And so that factorial part is chopped off, and then what's remaining is this 543, which is 543. So if you ever see this division, you might think, wow, what is that division doing there? So now that you've sort of seen this, what it is it's taking the 5 factorial, because that's sort of the origin or the beginning, and then by dividing by this smaller number, it's actually designed to chop off the tail, or chop off this excess, and just leave the 543 remaining. Okay, because the full factorial goes all the way down to 1. Okay, does that make sense? Okay, so if you have certain items and there's a subset, then it's permutation. If you're using all of them, then it's factorial. Or, you can just do it out the long way. You'll get the right answer. You'll get the same answer. You just do a few more steps, a few more keystrokes, right? Don't make an error. But if you can jump to the shortcut, then you should jump to the shortcut. Okay, permutation. So another permutation example, right? From n items, take a unique ordering of items, NPR. Suppose a club has 10 members, and it must select its executive committee of 3 officers: president, secretary, and treasurer. How many distinct executive committees are possible? So here, observation 1, it's 10 total, want 3 subset. Okay, so in other words, as soon as you make this observation, you rule out the factorial, right? If it was, 10 items, 10 members, and they're each going to be assigned a unique job. They're going on a hike, and one person's in charge of this, another person's in charge of that, and every single person is going to be assigned a duty on the hike. Right? Then it's factorial, right? Because each and every person has a specific job. And then, you can say, well, we have the leader, we have the person in charge of maps, we have the person in charge of water, we have the person in charge of, the radio or, whatever, snacks. We have 2 people in terms of snack, the first person and the second person. And it makes a difference. This is going to be, the dry snacks. This is going to be, some other snack, and so if every person has a job, then it's 10 factorial, right? But that's not this problem, okay? This problem is a subcommittee. So then you say, well, it's either the case where order matters or order doesn't matter. And then maybe you do observation 2, order matters. Right, say the first one we select is the president, the second one we select is the vice president, secretary and treasurer, So the second one is the secretary, and then the third one is the treasurer, right? So how many ways, right? There's 10, and then after you select one, the person's already the president, they can't have 2 jobs, so then there's only 9 possibilities left. Then those 2 already have jobs, and you can't have, repeats in the executive committee, then that's 8, right? So 9 times 8 is 72 times 10, so this is equal to 720, right? Of course, you could spot this as a permutation, 10 items, and you want to pick 3. So you do 10 items, and then right above the minus sign, shift minus sign 3, and that's the 720. Okay, so either way, the long way, right, where you figure out the stages, identify the possibilities per stage, and then just multiply them. That gives it to you. Otherwise, you have this. Oh, just for the sake of argument, we could say do 10 factorial divided by 3 factorial. So if we did 10 factorial, oops, have to do second factorial, 10 factorial divided by 3 second factorial. Actually, it's 6. I could have just punched in 6. Oh wait, sorry. 7 factorial, which is 10 minus 3 factorial. That's 7. Okay, sorry. So that's 10 second factorial, and then you have to divide by, wait, did I do that? 7 factorial, so that equals 720. So so it's P n r is equal to n factorial divided by n minus 3. So n minus r factorial. So the first time I just did the 3 factorial, but I should have done the n minus 3, which is 7. Okay, so that's sort of just the definition. Okay, and then the final special case, which is the one that's important for the binomial theorem, is this unordered case. Okay, and so now the case is the club has 10 members and it must select some subcommittee of 3 members. How many different committees are possible? So notice that when you're selecting the committee, you might select person A first and then person B and person C third, or you might select person A first, person C second, person B third. You might select B first, followed by A second, C third. So anyway, as you're selecting the committee, you theoretically, right, pull them one by one, right? However, once they're on this committee, whether they were first or second or third, it doesn't matter, right? And so you kind of get rid of that. And so what you actually do is you actually divide out by this permutation. So for example, before there were 10 committees and we selected 3. When we selected 3 in order, there were the 720. But now, if we're unordered, we actually take this committee size and divide it by 6, and that's actually what we get, right? If you do the 10, and then now combination or choose. Sometimes people call it choose or combination. 3. This actually gives us the 120. Okay, and so now I want to see if we can spend a little bit of time to try to figure out why does it make sense to divide out by these, right? And so, in a certain sense, when we do the first permutation, and order does matter, we pick these up, right? Where these are different, we distinguish among these. Now, for combination, we want to sort of wash that out. We say, okay, these 6 are actually the same, and so 3 factorial. And so what we do is we divide by them. Okay, so and suppose you have 3 items you want to arrange in a line, right? Suppose 2 of the items are identical, right? How many ways do you have, right? So here you had the 3 factorial, right, which is equal to 6. But if you have 2 of them that are the same, you have 3 factorial divided by 2, which is equal to 3, right? So you really see, because this one and this one are actually the same, right? This one and this one now, because you have the repeated elements, those are actually the same. And then this one and this one, those are actually really the same. And so what we did is we took our original permutation, where order does matter, and then we said, well, we have some repeated elements. In fact, we have 2 elements that are repeated, so we divide by 2. And so where we had 6 before, we really come down to the case where we only have 3 that are really different, right? So, imagine you have 4 factorial, which is 24. So it's not too difficult, right? So here's 4 of them, so 1, 2, 3, 4, 5, 6. So 6 times 4 is 24, right? So it's not too difficult to put all of them out there. And so suppose that we have 3 that are identical. Okay, so we'll set A equal to C equal to D, so that all that's different is A and B. Okay, and so in this one we set C and D equal to A. Right here we set C and D equal to A. Here we set C and D equal to A, right? And then so we always set C and D equal to A. And so you can see that this first row actually collapses into the same. This second row actually collapses into being the same. Same with the third and fourth. So really, we're only left with 4 different ones, right? So what has actually been made identical? And so here, if we sort of factor out or sort of leave the B in there, this ACD, we have ACD. So it's really ACD, which is that ACD. Here's A, C, and then D, which is that ACD. And so we're sort of pulling out the ACD, right? And so there's 3 items, right? And so how many ways are there to arrange the 3 items? 3 factorial is equal to 6, right? Basically 1, 2, 3, 4, 5, 6. And so where we started with the 4 factorial arrangements, the total arrangements, because we have 3 that are repeated, we divide by this 3 factorial. Okay, so anyway, the whole purpose of this is just to sort of help you feel a little bit more comfortable with dividing by these permutations. And so it's just to sort of file away to remember. You might remember that this CNR, which is also written as NR, has this kind of a definition, right? And so you should think that so you start with kind of order does matter, like you have, you know, this experiment, and so the first one is success or failure, the second one is success or failure, the third one is success or failure, and so here you actually have that kind of an arrangement. But then the successes, which ones are successes don't matter, and which ones are the failures, they don't matter, and so that's why this coefficient tells us the ones that don't matter. Okay, so anyway, it's all, if you didn't totally follow all of that, don't worry about it. It's just sort of a proof, trying to explain why. The bottom line is to remember that we have these. That's what it means. If the order doesn't matter, you use the C. Okay, so this is actually what the full, say, sort of binomial theorem is. And it really is a statement about if you have A plus B or X or Y or whatever, if you have any two items and you raise them to the nth power, they actually fall into a pattern. Okay, and so this is the pattern. Okay, and you could sort of think that the you know, there's an order that it has, and then you pull it out, and so it becomes unordered. Okay, and so sometimes when you see these big sort of general things, in order to try to make sense of it, what you do is you say, well, you know, do I really believe that? That seems to be so complicated. Let's try some simple cases. Okay, so if you set n is equal to 2, right, then instead of being n, it becomes 2. Everywhere you see an n, it becomes 2. So everywhere you see an n, it becomes 2. So there's no r over there, so it becomes n, becomes 2. And so here is just basically the same thing. It's just the different notation here, and here it's sort of in its full glory. That's what it looks like. At this point, you know, we're not going to do those. We'll continue with the sort of numerical form here. So now we have this summation thing to deal with. Fortunately, the numbers are kind of small, right? So you can see that r is going to go from 0 to 2. So r is going to take the value 0, 1, and 2, right? So this means r is going to be 0, 1, or 2. Okay, so the first time we go through, we have r equal to 0. Okay, so the first time we go, and then the second time we go through, we have r equal to 1, and then the third time we go through, we have r equal to 2. Okay, so if r is equal to 1, r equal to 0, then sort of this 2 gets copied over, this 2 minus 0, that collapses down to 2, and then here this r, remember r is 0, so it becomes 0 factorial. Okay, so this a to the r power, remember r is 0, so it becomes 0. And then we have 2, right, because it was n minus r, so we have 2 because n is 2, right, case n is 2, minus r, so that becomes minus 0. Okay, so the second one, the 2 stays, and then, oh, sorry, this should be 1. Sorry, this should be 1. So those should change to 1. Oh, sorry, I forgot to flip these. So this should actually be 0, and that should be 2. But it doesn't matter because they're flipped around, right? But anyway, r becomes 1, and it becomes like that. Okay, so then, you know, we could simplify it, but we'll do that in the next line. Meanwhile, for this line, let's finish it off by setting r equal to 2. Okay, and then when r is equal to 2, oh no, that is right. Sorry. We do have the 2, right? And then we have the 2 minus 2. So the 2 minus 2 becomes r. Okay, so now this r has become 2, and then the b is 2 minus 2, right? So basically you can see how when r is 0, the power of a starts out at 0, and then the next one it's a to the first power, and then becomes a squared. And then here, b with r equal to 0 starts out with b squared, and then now the power of b falls down to 1, and then now the power of b falls down to 0. Okay, so basically this coefficient becomes 1, right? A to the 0 power is 1, so we can omit it, and we just have really b squared. Next one over, this is 1 factorial and 1 factorial, so they become 1. So they really, and 2 factorial is 2. Okay, so we each have a and b coming in with the power 1, but there's 2 of them, and so the coefficient tells us that there were 2 of them. And then finally, this is 0 factorial is 1, and then 2 factorial over 2 factorial is 1, right? Because anything over itself is 1. And then we have the a squared. Now we have the b to the 0 power, and so anything to the 0 power is 1, so we omit it. So we have this, and so finally we have this result that a plus b squared is equal to a squared plus 2ab plus b squared. And you might say, well, I already knew that. And the answer is, well, you sort of memorized it, right, and multiplied it out. And here we actually have this sort of general formula that gives it to us. Okay, so the next one up, n equals 3. You might remember that a plus b cubed is a cubed plus 3a squared b plus 3ab squared plus b cubed, right? And so if you didn't remember that, or you didn't know that, you could simply do it directly, multiply the whole thing out. But it's also possible to get it from the theorem, and so we'll just go that very quickly. So here n is equal to 3, and so r goes from 0 to 3. So this time r is equal to 0, 1, 2, and then we add in 3. So there's the 0 term, the 1 term, the 2 term, and then the 3 term. Right. So again, here with 3 is constant for this instance, and so we're ranging over r is 0. Okay. Now r is 1, and so now the a, you can see the a is increasing, and the power of b, exponent for b, is decreasing. Now the coefficient bumps up from 3.1 to 3.2, and then the power of a increases and the power of b decreases. Then here again, the coefficient, we have the next one over, the final one in the series, and then the power of a has gone all the way up to 3, and then the power of b has come all the way down to 0. Okay, so now b to the 0 power is 1, so we omit it, and then we can see that, and b, yeah, or b, oops, no, it's okay, right? Oh, sorry, this should be a, yeah. A cubed, b cubed, no, I think it's right. Yeah, b. Right. So the power of b has gone from 3 to 1, 0. Sorry, yeah. And the power of a has gone from 0, 1, 2, 3. Okay? And so then maybe you remember these coefficients are 1, 3, 3, 1. But if not, you can just work them out, right? And so that's how it works. And so we, it seems reasonable. We haven't totally proved it, right? But it seems reasonable that this is the expression for all of those cases, right? So let's see if we can see an example of this, right? So hopefully this will work, right? Yeah. Okay. So yeah. So here, let's look at A. Let's pretend that this 2 piece is our A, and this is our B. Okay? And so what we want to look at is we want to look at A plus B squared, right? So this would be A plus B over here, and then this would be times A plus B over here, and then the area of that would be a plus b squared, right? So if this is a, right, here's a squared, so this is a squared, okay? And then if this is b, then this is b squared, right? And so clearly you can see that a plus b squared is not, a squared and b squared, right? It's not enough, right? You actually need these pieces, right? Because these pieces are a times b, right? If this is a and this is b, this area is a times b, right? And so here we have two of them, right? A times b. So we have a squared plus 2ab plus b squared, and that is equal to a plus b squared, right? And so, here we have them in a particular order, right? We need them in a particular order. We need, the b this way and then a that way, and then we need a that way and b that way, and that's how, in order to really have it as a square, the order matters. If we had it like that, you'd say, well, I believe that that's a square, but it's not a square, right? Because the order is important. Okay. So on the one hand, if order is important, then it has to have that orientation, because, but at another level, sometimes when you're focusing on something else, you have a squared plus 2ab. This is 1ab, a and b, and this is another ab, and this is your b squared, right? So this is a squared, this is a times b, so two of them, and this is your b squared. So this is a squared plus 2ab plus b squared, and that, as you saw, right, is equal to, this is a plus b squared, right? Because we have a plus b on this side, and then we have a plus b on that side, right? So that's a plus b squared. And as we saw, you can decompose it into a squared plus 2ab plus b squared. But you already know that, right? So this is just another way to look at it. So we could continue, right? If we have this cube thing, right? So this is a cubed, right? And so we have, so that's a cubed. This is b cubed, right? So we have, on this side, we have b squared, and then we add a dimension, so we have b cubed. And clearly, if we try to cube it, the cube of a plus b, should be kind of like that, right? So if we have these, excuse me, other pieces, those can help us, right? So this one is a squared times b. Okay, so these rectangular pieces like that are a squared times b. These are b squared, so here's b times b, and then this is a. Okay, so these are a squared b, and then these are b squared a. Okay, so we can arrange these kind of like that to help us get started, right? But that's clearly not a plus b cubed, so we can actually put that one, say, on top, and then these two on the side, and then finally, if we have this third one there, then we have the a plus b cubed, right? We have a plus b cubed, right? So this is a plus b cubed, where order does matter, because as you can see, there are all the pieces are all in a the yellow and blue rectangle kind of pieces are kind of in a very, very particular orientation, and they have to be in that particular orientation in order for the a plus b cubed to work. On the other hand, if order doesn't matter, we want to sort of look at the composition, then we can say, oh yeah, we had an a cubed. We had, let's see, here, this is the one with a b squared. So these are the a b squareds, No, sorry, I want a cubed. I want a squared b. So these are the a squared b, right? And so here are the a, and then a, and then b squared. So those are my a, b squareds. Okay, 3 of those, and then I have my b cubed, right? So a cubed again. So right, so a plus b cubed. Right, here's a plus b cubed. What is a plus b cubed? Right, if order doesn't matter, right, a plus b cubed is a cubed plus 3a squared b plus 3ab squared plus b cubed. Does that make sense? And so obviously it's a little hard to go into the four dimensions, but you can kind of see how sometimes, order does matter, and then, you have that case. On the other hand, sometimes, the order doesn't matter, and then you can arrange like with like, and then, here's 3 a squared b, and then 3 a b squareds. Okay? Does that make sense? So now that we've sort of expended the energy and gone through to understand this, let's see if we can use it. Okay, so how do we use it? So here's this, this tool, this theorem, this formula, and it's, mathematical. And so we can use it to understand mathematical things, right? So suppose we want to prove that the probability mass function of B and P always sums to 1. Right? How could you prove that the probability mass function of the binomial distribution always sums to 1? How could you prove that? So we have this tool, this formula. So that's our starting point. And what we'll do is we'll say that A is equal to P, this probability of success, and we'll say that B is equal to Q, the complement, 1 minus P. Okay, so if we say A is P, we get that. If we say B is Q, we get that, right? And then we'll sort of ignore these, which are just the same, and we'll just concentrate on this one. And so we have, just copy that over, copy the coefficient over, but now A is equal to P, and Q is equal to N minus R. And, oh, by the way, if you look at this, you should say, hey, that's the probability mass function, right, for the binomial distribution for B and P, right? Or I should say, these are each of the terms, right, where there's, if say R is equal to 0, if R is equal to 0, then we kind of start the other way, right? So the probabilities all will go away. R will be 0, so this is Q to the N. So now we have the successes, the Q, the failures, only failures, and then, but we would have only one of them, right? Because if R is equal to 0, we know that the N0 is always 1, right? So we only have one of those. And meanwhile, if we say that R is equal to N, we have N, okay? And then we have 1, the coefficient becomes 1. P becomes to the N power, Q, N to the minus N becomes 0, and so the Q goes away. And so now this is where we have all successes, and we don't have only one of those, right? And then each of the other terms, depending on how many successes, you have the successes to the power of the successes, and then you have the failure to the power of the failures, right? And then remember, it's kind of symmetric, right? So here's a peek at Pascal's triangle, because we kind of saw that by looking at the other one, right? So this is actually adding up all of the terms in the binomial distribution, right? Now, of course, we remember that Q is equal to 1 minus P. So when we plug that in for Q is equal to 1 minus P, P minus P is 0, and so we're left with 1. So 1 to the nth power is 1, and so what we're left with is the statement that the sum of all of the probability mass functions terms is equal to 1. Isn't that cool? Anyway, that's why some people get excited. It's almost like going to a museum when you see these things. So you look at that, you go, yeah, that's nice. But what's next, right? So you go on to the next painting or sculpture in the museum. Another thing that we can do with the binomial formula, binomial theorem, is we can find the sum of one row of Pascal's triangle. So what do we mean by that? So remember this Pascal's triangle thing. So there's different stages, like we'll call this the 0 stage, the first stage, the second stage, the third stage, and so forth. And what we can do is what we want to do is we want to find the sum of one row of Pascal's triangle. So if we add up that one, that's the trivial one, right? The first stage is 1 and 1, so that's 2. The second stage from the quadratic is 1, 2, 1, right? So this is like x squared plus 2 xy plus y squared, you know. So the 1 plus 2 plus 1 is 4. Okay. We just saw this 1, 3, 3, 1, right, for the cubic. So this would be like, you know, x cubed. This is like 3x squared y. This is 3xy squared. And then this would be 1 times y cubed, right? So, but you just add the coefficients. So, you know, 1 and 3 is 4. And then 3 and 1 is also 4. So 4 and 4 is 8. Okay, so now we want to, of course, do this in general and add them all up. So if you start with the binomial expansion theorem, you might scratch your head for a while and say, how could we use this, right? And so you would say, keep n as it is, but just set a and b equal to 1. Because the formula applies all the time. Like whether you set it equal to a equal to p or b equal to q, it's always true, right? So for sure, we can set a equal to 1 and b equal to 1. And look what happens when we do that, right? So you have a is 1 and b is 1, right? And now a is 1 and b is also 1, okay, for however you want to do it. So what's 1 to any power? 1 to any power is 1, okay? 1 to any other power, it's a different power, but still, a 1 to any other power is also 1. Right, so the a and b exponent stuff basically goes away, and so we flip this around and bring it to the other side, and 1 plus 1 is obviously 2, and we have 2 to the nth power. So basically, from the binomial theorem, we can see that the sum of one stage across a stage is actually equal to 2 to the n. So we always know that it's 2 to the n, and also. Remember that we started to look at this with the coin tosses, right? Like n tosses of a coin, 2 tosses of a coin, 3 tosses of a coin, right? And so whenever you have the tosses of a coin, the binomial coefficients, Pascal's triangles, helps you sort them out as to how many are repeated. Remember that? It's like if you count the number of heads, like the ways that you get 2 heads in 3 tosses of a coin, how can you get 2 heads? There's 3 ways, right? If you have 3 tosses of a coin, how many ways can you have 1 head? There's 3 ways to do that, right? And so 3 tails, there's only 1 way to get 3 tails and 3 tosses of a coin, and then 3 heads, there's only 1 way to get it. And so this gets all of them. Okay, so there's this link between this binary experiment, heads, tails, success, failure, Bernoulli trial, Bernoulli events, and adding them all up to the binomial distribution. I mean, in fact, that's because there's this binomial theorem, and this expression is related to those probabilities. That's kind of why it's called the binomial distribution. Okay, so oh yeah, this is the example that we kind of went through last time, but maybe it's helpful to just revisit it with this sort of binomial theory. So here is that probability mass function, right, in general. And as long as P is a probability and Q is 1 minus P, the complement, these will always add up to 1. With whatever P, whatever value for P, whatever value for Q, I mean, not whatever value for Q, whatever value for P, because that will set the value for Q, right? And so as long as Q is related to P that way, then it'll always be a probability distribution. Okay, and so here is kind of how the coefficients, and then here we're still leaving the probability of success as it being in general. Here obviously is where we have specified it to 0.6. So this would be B5 and then 0.6 that we saw before, right? And so, oh, wow. Let's see. We also thought that it would be helpful to look at some binomial distributions, right? So here in this other PDF that's up there, there's this kind of gallery of the n of the basically certain fives. So this is the binomial with 5.1. This is the binomial with 5 and 0.2. This is the binomial with 5 and 0.3. This is binomial with 5 and 0.4, 5 and 0.5, 5 and 0.6, 5 and 0.7, 5 and 0.8, and 5 and 0.9, and then that's the end. So this is what this is sort of a tour of one of the subfamilies, or some of the, of the 5 binomial. Again, one of the quantities, or one of the ideas that's actually very important, as we'll see when we deal with distribution, is what is the mean, and then the variance. Here, instead of the full variance in its full glory, we actually have the standard deviation, which you recall is the square root of the variance. Okay, and so what we also have is the mean minus 1 standard deviation, and so that's the value. And then what's the mean plus 1 standard deviation? Okay, so if you the Excel homework that you have, the Excel assignment, is actually to kind of just do this, actually. And so there, in the homework you'll find that there's a particular BNP, just one BNP. And so what it says is basically use the Excel binom.dist. Okay, so this is the Excel binom dist function, right? And so the first value is this one, and then the second value is those, and then you say false to get the probability mass function. Okay, so college course, you want to say prove it, or how do you know that? How do you show that, right? So basically, what you want to do is you want to basically compute the coefficients. And so if we go back, go back to our notes here. Go back to our notes here. The this is the expression for the probability mass function, or maybe I should go back and say really this is the expression for the probability mass function. Right? This is really you add up the first term, the second term, the third term. So this is kind of a little bit abstract, right? If we set n equal to 5, right? If we set n equal to 5, then we have this one over here, n equal to 5. So this is kind of the full probability mass function for all of the ones where n is equal to 5 in the binomial distribution family. Okay, so you would add, if you added this one plus this plus this one plus this one plus this one plus this, you get 1. Okay, so now if we switch to our gallery, This is sort of the vertical view of that, right? And then we want to say, well, let's just verify this formula. And so this is the combin function. There's a combination function where you put in n and you put in r and you get the coefficient from Excel. And so here what we do is we take the probability of success and we raise it to the 5th power. So we basically take 0.1 to the 5th power. Okay? And then we take q, which is 0.9, and we raise 0.9 to the 0 power, right? Because r is equal to 5, and 5 minus r is equal to 0. And so when we raise 0.9 to the 0 power, we get 1. So now we take the coefficient and we multiply by the probability, the total or the and intersection of all of the successes and now the failures, and we get this. And so that's actually equal to that. Okay. So the second coefficient, here's what Excel binom dis spits out for the probability mass function. Prove it. So here we take the coefficient, which is 5. Here we take the probability of success 0.1 to the 4th power. Okay. Now we take 0.9 to the 1st power. Why do we do that? Because r is equal to 4, and probability raised to the 4th power is 0.1 to the 4th power, and then now we have q coming in at the 1st power. So now we multiply those all together, and then that's the coefficient. Okay, so you'll basically just do this for once for the homework, and then here it is for the next coefficient down the line. So this would be C53, right? C because n is equal to 5 and r in this row is equal to 3. Okay. Now we have the probability of success is cubed, 0.1 cubed. We have 3. So the sum of the powers equals 5, right? So here's 2. If this is 2, then this is 3. So this is 0.1 cubed, 0.1 squared, right? This is cubed, this squared. Now you multiply all those together, and then you get which is the same. Okay, and same thing here. The next coefficient down here, now we have 0.1, r is 0.1 squared. So now we have 0.9 cubed. Okay, and so we multiply all together, we get that. And now we have the case where r is equal to 1. We have 0.1 raised to the 1 power. Now we have 0.9 raised to the 4th power, and we have this coefficient 5. Multiply those together and we get that. Okay, so and then this is just sort of plotting the CDF, cumulative distribution function. Okay. So this is what it looks like, and so you can see that if the probability of success, right, the number of successes, the probability that the number of successes, that you have 5 successes, if it's a 0.1 rate, it's really low to have any successes. Most of your cases will be what's considered failure. The mean is actually 0.5. So the mean would be over there, and the standard deviation is 0.7. So most of the distribution is actually between this mu and then this would be minus sigma and this would be plus sigma. So you can see that most of the mass, of course, here negative, and there's nothing on the negative side, right? But most of the mass, most of the probability is on this side, with the 0 and the 1. So you add the 0 and the 1, you get over 90, right? Because this is 32 and this is like 0.6, so you're getting like 0.86, right? So 0.9, you're getting around 0.9 is between here and here. Okay. So next one in the family, 0.2. So you can see how we'll just go through these and then come back a little bit, right? So you can see how the peak shifted, or how this is for 0.1. Now this is for 0.2, and you can see that the mean, right, NP, right, 5 times 0.2 is 1, okay, and then if you do NPQ, you do 0.9, and then you take its square root. No, 0.8. Yeah, which is like 0.81, and so you take the square root, you get about 0.9. So there's a little bit of rounding over here, right? So the mean is over here at 1, and then the standard deviation is just under 1. Okay, so most of the distribution is actually over there, right? Technically speaking, this does not include 0. This does not include 2. So technically speaking, it really only includes 1 point, which is 0.4. But if you do rope in and include 0 and 1, you've got 0.6, 0.9. So you've got about 0.8 or 0.9 of the probability in there, right? And then here, the cumulative distribution function just sort of takes these big jumps, and then it really kind of gets closer and closer to 1. Of course, finally it does get to 1 down at the end. Okay, so here's this one really just crammed all the way to the left. Now it's shifting a little bit over to here, the probability of success 0.3 now, and NP 1.5. The mean is 1.5. And standard deviation is actually 1 now. So it captures 1 and 2. So 1 and 2, between 1 and 2, if you add those up, that's like 6, 6. So these guys have like 66% of the probability is within this mean and 1 standard deviation. So between the mean, this interval of the mean minus 1 standard deviation and the mean plus 1 standard deviation. So that's where most of the probability is. Okay, and so that's the 0.3. If we go over to 0.4, now you can see it's really shifting much more to the middle. The mean, where's the center of this distribution, NP? It's 2 now. Mu is here. And then the standard deviation is 1.1. So it's a little bit more spread out than the other ones. So between capturing all of these probabilities, you have, these are like a quarter. So those together would be like a half, and then you add 0.3, so you're like between um, 89%, 89% or so, 90% of the probability is within this mean plus and minus standard deviation. So with this region of the mean plus and minus 1 standard deviation, you can see the probability there. So here's the symmetric case. This is the perfect coin toss case where it's 50-50. Symmetric mean is right in the middle, right? Half of 5 is 2.5, right? 5 times ND, 0.5 is right in the middle. Again, the standard deviation is 1.1, so you get to 3.5. And so if you capture these two, say 62%, 62 of the value is within this mean from low 1 standard deviation to high 1 standard deviation. And then the steps are a little bit, that one is the same, that one, a little bit more, and maybe not. Some are so small, and then here, if you look at the other, some are so small they're really steep. Here they're more even. And then really the 0.6 is where it just starts to mirror over, right? From one side to the other side. Okay, and so that's the last one in the set. Okay, so that's kind of how the changing in the probability sort of affects the shape of the distribution. And generally, as you want to try to understand a distribution, you concentrate on what's the mean. And so here, 5 times 0.8 is 4. So here's the mean. And then the standard deviation. In this case, we get the variance, which is NPQ. And then take the square root of that to get the standard deviation. So that's 0.9. So we're going from 3.1 to 4.1. So really, we're just including this 1.4 that's 0.40. But if you kind of include sum of the 3 and sum of the 5, you can kind of get, you see most of the distribution is kind of in this area, and then this is out, you know, people would say consider that like a tail, because there's very, very, very little probability out there in the tails. You know, here in this more symmetric one, the tails are, you know, further out, say, if we're looking at continuous probability. Here there's no real tails because everything is compact. But next week, when we look at the normal distribution, you can sort of kind of, right, that famous bell-shaped curve, you can sort of kind of see the famous probability distribution there, which is why some of the concepts that we learn here, distribution, something to sort of go over to the normal distribution for next week. Okay, does that make sense? Okay, let's see. A request to review a mortgage problem today. You know, we do, part of this course is preparing you for Business 310, which is basically business statistics. I think it's called statistical analysis for business decision making or something like that, but it's really business statistics. The other goal of this class is to prepare you for 314, which is business finance, and the time value of money concepts are very important there. So we'll look at this mortgage problem. It really is, I should say, an annuity or amortization table. Really, annuity plus amortization. Oh, let me put this on. Yeah. Amortization table. Okay, so these fellow fell in love with a hill that had a small cottage with a charming well. They decided property and needed a year mortgage for $350,000 with fixed 3.8% interest rate. Because this is their personal residence, there's a possibility that they may be able to deduct all or part of the amount of interest that they paid. If they start their mortgage on October 1st, how much interest did they pay in the first calendar year? Generally, right, personal income taxes are paid on the calendar year, right? From what did you earn from January 1st to December 31st? So you have until April 15th the following year to sort of organize it and tally everything up and file your tax return. But the period of the return that it's covering really the calendar year for most people, right? January 1st through December 31st. So the question is, you know, how much, if you start this mortgage, how much interest did you pay? Because you could deduct it, right? There's a possibility. So that's why you might want to do that. So, you know, you read this problem, you say, oh, it's not a cost volume profit problem. Right? There's no probability here, no binomial distribution. There's an interest rate. Compound, you know, it doesn't say compounding, but this is a time value of money problem, right? So when you think of time value of money problems, how do you do them? What do you start out with? That table thing. right? And so the first thing that's lurking in the background is the interest rate, sort of in compounding of interest rate, and number of periods I. So these are sort of the three kind of environment of the TVM problem, time value of money problem. And then there's the cash flows, PMT, and then FV. Remember, right, this is a mortgage, right? And so the whole purpose of the mortgage is to pay off the debt, and so by the end, there's nothing left. Clearly, right, what is the monthly payment, the annuity portion of the payment? That's what we have to figure out. So when you read this problem, it's a 30-year. So we know it's a residential mortgage, right? And so I should say the first row is always the annual row. We know that it's a residential mortgage. Mortgages are monthly, right? And so here, this one is a 30-year mortgage. So in the annual row, we put 30 years. And then this is this nominal interest rate, the main interest rate that's given. And then, of course, they need to borrow $350,000. It doesn't say what the purchase price is. Usually, you have some down payment, or maybe you have a second mortgage. But anyway, we'll just talk about this one. Okay, so in order to really go forward, we have to know the number of actual compounding periods, right? If 30 years and they're making monthly payments, 30 times 360. So there actually are 360 compounded. Okay, this is the nominal interest rate if you borrowed for an entire year. So over 12 months, right? Over one month. Well, you pay a 12th of that, which is 0.4%. Okay, and then you're actually good to go, right? So you pull out your calculator or Excel, clear TVM, right? And so N we know, N we know is 360. So that's the number of compounding periods within each of the compounding periods. It's 0.4% interest, right? And I want to, I'll just put in 350,000 as our PMT. Let me recall that the future value is 0. Not surprising, we did the clear TVM. So we want to compute the PMT. Okay, and so our monthly 1836.33. Okay, so the PMT so now how do we deal with this amortization table, right? So once we have the TVM registers filled out, we can go to the amortization table, right? And to get the how do you get the amortization table, right? So you take the 350,000 and you multiply it by 0.4, right? So if you let me sort of step out of this here, and you take the 350,000. Oh, actually, I think I can do recall of PV. Right, so that's 350,000. So just going to equal. So put it in a sort of computational register. And now what we want to do is we want to multiply it by the 0.4. No, that's 0.4%. Right. So I need to recall the PV and then equal. And then I want to multiply it by 0.4%, so 0.004. So that's the decimal of 4%. And so that's the amount of interest that's owed. And since this was the actual PMT, right, this is the amount that you send in to your mortgaging service firm. And what they do is they say, well, we all agreed that we're this nominal 4.8% interest. So the monthly amount that you owe is $1,400. So that's the interest that we pocket. But this leftover amount, right, is now going to pay down the principal. And so the next time you have to make your payment, the interest rate is still fixed. However, because the remaining outstanding balance has decreased, that amount has decreased, your payment is fixed, and so the excess payment actually increases. So you slowly start to fill this more, right? So if your first payment was in October, your second payment is in November, and your third payment is December. Is that right? If they started the mortgage first, they made this amount of interest payment in the first month, October, this amount would be November, and this amount would be December, right? Because it's a partial year, right? So this is the amount of interest that they paid. Okay, and so on the financial calculator, if you are in the amortization worksheet, if you set the P1 equal to 1, and you set the P1 also equal to 1, so I'm going to go up. P1 is, so my beginning, my top that I want to see is 1, and my bottom that I want to see is 1. Actually, I'd like to go through it backwards. But you can see that the interest amount is $1,400. The excess principal is 436, and then it tells you what the balance is. So now what I'm going to do, this is not really how you use, how you really make this part of the calculator sing. But what I'm doing here is, as you can see, I'm doing the P1 is equal to 2 and the P2 is equal to 2, right? So now I'm basically taking my upper pointer to look at row 2 here, and then I'm taking my lower pointer to look at the same row. So now I'm just looking at the second row. So this is not really how you'd use the amortization worksheet in the calculator, but you can see that it actually does give me the second row, right? And then when I go here, this is the excess principal, and so forth. Okay, so really the way that you use the calculator is you want to say, I want to know 3 months of interest. So what I do is I put in 1 and enter, and then I put in 3 and enter. Okay, now when I go through this, this tells me that over the 3 months, this is how much interest you paid. Over the 3 months, this is how much principal you paid down. And then this is how much you have outstanding for the next goal. Okay, and then for the next calendar year, we would do, I think, 4 plus 15. So for the next year, you'd put in, say, 415, and then because it would be, that would when you have 12 months as a full year. Okay, so be very careful in the beginning and the end, because then you have the partial years. That's good. Okay. So have a good weekend, right? And we'll see you on Monday. Let me still fix the homework a tiny bit. So don't do the homework yet. I want to fix that last problem a little bit, and then I'll email you when it's ready to go. Thanks.